So this video is about calculating work, and it's an introduction before we get to integrals with it. So our work here is just force times distance. So what is force? So you can think of a force for what we're dealing with, which is with just gravity, that this guy is applying a force to him. So him hanging here, that is the force that he is applying to this guy hanging. What work is how much work is needed to pull him up to the cliff. So to do that, we multiply force times distance. So let's try one. So we have how much work is done lifting a 1.2 kilogram book off the floor to put it back on the desk that is 0.7 meters high. And then we're going to use the fact that the acceleration constant for gravity is 9.8 meters per second squared. So if we take our mass, which is the 1.2, and we multiply it by 9.8, our calculator tells us it's 11.76. And then the unit we use is newtons. So instead of saying kilograms times meters per second squared, we just say newtons. Okay? Now the work. The work is now the force times the distance you have to move it. So we put our newtons in there. Our 11.76 is our force, and then we multiply it by the distance we need to move, which is 0.7 meters. And always make sure that this is meters if that's meters per second, and then it's going to be meters per second squared, so we need to make sure it's always in meters. Plugging that in our calculator. So we really just have to calculate force, times it by distance, and we get 8.232. And now we just put our units on there. So the first one was newtons, and the second one was meters. So it's newton meters. And there you have it. There's your work. So let's try one with American units. And they're going to get tricky like this. So it says how much work is done in lifting a 20-pound weight. So when they say weight, they're not saying it's a mass. They're saying that acceleration's already been thrown into it. So we do have gravity at 32 feet per second squared, but we don't need to use it. So our force is already given. It's 20 pounds. So if you notice with American units, we use foot-pounds. So our work here would then just be 20 times 6, which is 120 foot-pounds. And that's it. But the same thing needs to be applied. We have feet, we need feet. So 120 foot-pounds. Now let me explain how this works with an integral. So I've plugged in 20 here, so this is our height. It's a constant force as we're being applied for that entire 6 feet. So the way you can kind of look at it is that work is still the force times the distance. So if you think about our rectangle, the height of our rectangle is 20 and the width is dx. So this would be our integral of 20 dx from 0 to 6. So if we take this integral, we get 20x, we plug in 6 and 0. So you can see that's our distance and that's our force. So the way I like to look at it is you can kind of think of these as very, very small forces. So I'm going to make my rectangle a little bit thinner. So there, so you can think of it like, oh, we're just tapping these all the way through here, and then we're adding up all of those forces that we're applying from 0 to 6. So that is the work that is being applied to move that weight through 6 feet. And so in the next video, what we're going to be doing is changing this. It won't be a constant, it's going to be a variable. But you can see it's just a rectangle with a constant. So what is the area of this rectangle? Well, it's 20 by 6. It's the force times the distance. So it's just the area of a rectangle. That's all it is.